Okay, so chapter 1, section 6 deals with the units of measurement. And I'll put a point here. If units are important. If we're going to measure anything, which we do in science and technology, that's what we do, we measure things, we have to agree on what the terms mean. Let me go to the next slide. I'll come right back to this one. It turns out in 1999, there was a Mars orbiter called the Mars Climate Orbiter, and it was $125 million. This was lost in Martian atmosphere in 1999 because two groups of engineers failed to communicate with each other about the units that were used in their calculations. So one group of engineers did some calculations, sent their results to another group of engineers. They were using different units. They were very close, by the way. It was actually, I think, English newtons and American newtons, which are extremely close to each other, but not close enough. And it turns out, because of their difference in calculations, this space probe was lost. So you can imagine what a disaster that must have felt like for those engineers. What a disaster. So we go back to units. Units are important. If we're going to measure anything, we have to agree on what the terms themselves mean. So we've got some standard units in chemistry and physics. And the dimensions that I want to deal with here are these four: length, mass, time, and temperature. The unit that we use for length, as you can see, is the meter. The unit that we use for mass is the gram or the kilogram. For time, it's seconds, and for temperature, it's kelvins. Sometimes we use degrees Celsius. We'll talk about that in just a minute. So to give you a couple examples of what these length scales or mass scales, where they are, let's look at some of these. I forgot about this slide. As we just said a second ago, length is meter, the mass is kilogram or gram, time is seconds, and temperature is kelvins. There's three other dimensions that we won't be talking about right now. So what's a meter? Well, if you get a pretty good sized basketball player, he's probably about 2 meters. I don't even know who this is. So about 2 meters. It's close to 6 feet, a little bit more than 6 feet. Another demonstration of that, you probably have seen a yardstick or a meter stick at some point in your life. As you can see, a meter is just a little bit longer than a yard, right? So 2 meters means that guy's, we saw on a previous slide, is a little bit taller than 6 foot. It's about 1.1 yards. There's a meter stick and a yardstick. Gram, to give you a sense of how big a gram is, a nickel is about 5 grams of an element. You know what the element is? Nickel, right? So a 5-cent piece in American currency is 5 grams of nickel. That give you a little bit of a sense of what a gram is. On the temperatures, we'll talk about this for a minute, a couple slides. It turns out that we have 3 different scales that we use here in the United States a lot: Fahrenheit, Celsius, and Kelvin. The standard unit is kelvins, but it's tied pretty closely to Celsius because they have exactly the same differences between degrees, right? So from 0 to 273, how many kelvins between 0 and 273? It's 273. How many kelvins between 0 and minus 273 for Celsius? It's also 273, right? How many degrees between boiling and freezing of water? 100 kelvins. How many degrees between boiling and freezing of water? Here, also 100, right? So both of these are pretty similar. It's just they're off by an absolute number of 273. Fahrenheit, on the other hand, has got a different size of a degree. So the difference between freezing and boiling of water in Fahrenheit is 180 degrees, right? So there's more degrees in Fahrenheit between boiling and freezing of water. Remember, we'll use these 3, and then we've got some formulas that we'll use to convert between these 3. You can see that the formula for Celsius to Kelvin is pretty simple. Just going to be taking Celsius and adding 273 to it to get kelvins. But that for Fahrenheit is a little more complicated. Okay, so just to give you a sense of some temperatures that you could identify with in Celsius, the temperature in the room you're sitting in right now is probably about 22 degrees Celsius. What is it in Fahrenheit? Well, of course, I don't know what room you're sitting in, but it's going to be close. It's going to be in the low 70s. It's likely to be 72 or 73, maybe 74 degrees Fahrenheit, but in Celsius, it's 22. What about a cool day outside? A cool day outside might have a temperature of 10 degrees Celsius. And freezing water at 0 degrees Celsius, right? Boiling is 100 degrees Celsius. Hot day, a summer day in Death Valley, is 40 degrees Celsius. Body temperature is 37 degrees Celsius. Okay, so that gives you a little bit of a sense of what the temperatures are in Celsius. And then I think what we're going to do now is look at some problems, or let's look at some factors, multipliers. So a kilo, we're used to these ones down here, right? A kilogram is 1,000 grams. A kilogram is 1,000 grams. A megagram is 1,000,000 grams. So mega means 1,000,000. Kilo means 1,000. Deci means 0.1. We won't use that very often. Centi means 0.01. We use that for centimeters. I think that's all we use it for. We never say centigrams or centiliters. We say centimeters though. And milli means 1/1000th. Micro means 1/1,000,000th. Right? Nano means 1/1,000,000,000th. Pico means 1/1,000,000,000th. Femto means I don't know what that is. Right? Giga means 1,000,000,000. Tera means 1,000,000,000,000. And peta means more. Okay, so these are your multipliers. And we'll be using these in calculations. I think we've got a sample calculation coming up here in a little bit. Okay, so next we have some derived units. That is, units that are not standard units. And the derived units are volume. And volume is base times width times height, right, of a regular object, of a rectangular regular object. And density is mass divided by volume. Okay? So some common units and their equivalents. 1 kilometer. It's really kilometer, I guess, but when, and we would typically say kilometer. That's 0.62 miles. 1 meter is a little bit longer than a yard. Like I said earlier, about 1.1 yards. 39 1/4 inches, or not a fourth, sorry, 39 1/3 inches. 1 foot is 30.48 centimeters, and that's exact, by the way. Here's one I would expect you to memorize eventually. 1 inch is exactly 2.54 centimeters. Okay? These ones we don't use so often. We'll use them, but usually when we use them, we'll be given the actual numbers in a question stem. 1 liter is 1,000 milliliters, which is also 1,000 cubic centimeters. By the way, that means that these are 1-to-1, right? So 1 mil is a cc, or a cubic centimeter, or a centimeter cubed. Excuse me. And then 1 US gallon is about 3.8 liters. Or to be, excuse me, to be more precise, 3.785 liters. Okay, let's look at some density numbers. Charcoal from oak has a density of about 0.457 grams per cubic centimeter. Ethanol, right, which is a minor component in gasoline sometimes, primary component in vodka, is 0.789 grams per cubic centimeter. Water is 1, right? So this would float. Ethanol and ice would float. I guess you know that from your own experience. Ice, the density of ice at 0 degrees Celsius is 0.917, so it floats on water. Ethanol would float on water. Charcoal would float on water. Sugar would not float on water. That would sink to the bottom, right? Sucrose, that's table sugar, 1.58 grams per cubic centimeter. Table salt, more dense than sugar, right? That sinks to the bottom of water, 2.16 grams per cubic centimeter. Glass is 2.6. Aluminum, that's a metal, 2.7. Titanium, another metal, 4.51. Watch this. This is amazing. Iron, 7.86. Now, that what you would say is pretty dense, right? Looks like copper's more dense. Lead is more dense yet. And mercury, which is a liquid, is more dense yet. This is the shocker here. Look at that, platinum. 21.4 grams per cubic centimeter. Wow. Platinum, 21.4 grams. That's very, very heavy for a little piece of platinum. Okay. All right, so let's do an example together. And I'm going to use my pen here, which is not really used to using this here. So let's see how this works. Converting between temperature scales. Now this is done for you in your book. But I want to do it out loud and manually. Okay, this is on page 16. Page 16. All right. So if you want to follow along, really the best thing for you to do is do it independently, and then check your work against mine. My advice to you right now is to pause this video, to work out this problem to the best of your ability, and compare it to my solution. All right, so a sick child has a temperature of 40 degrees Celsius. Temperature is equal to 40.00 degrees Celsius. Okay, what's the child's temperature, first of all, in Kelvin, and then in degrees Fahrenheit? All right. So if we're going to do this to Kelvin, we've got to find a formula, and the formula is given for you on page 16, right where you would expect it. On page 16, you're given a formula, and the formula to get kelvins is equal to Celsius plus 273.15. Okay, so what we're going to say then, well, we're looking for Kelvin, and we already know Celsius is what we're given, so we just plug that in there. 40.00 plus 273.15. You add those together, and you get, let's hope I got this right, 313. Oops, need a 1 in there, 15, and that's now kelvins, right? So that's the temperature in kelvins. Go real slow so you can read my writing. Okay, there's it. There's the answer to part A. All right, so let's look at part B now. For Fahrenheit, we know that the formula we're given on page 16 is degrees Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8. Okay? Well, we're looking for Fahrenheit, so I have to rearrange this equation. I'm going to say 1.8 times C is equal to Fahrenheit minus 32. And I'm looking for Fahrenheit, so I got to go, all right, well, Fahrenheit then is going to be 1.8 C plus 32, right? Okay, so 1.8 times 40, getting a little messy here, plus 32, okay, is going to equal to 1.8 times 40. I can't do that in my head. I can't do it anywhere. I'm going to do it in my calculator here. 1.8 times 40 is equal to 72. 72 plus 32 looks like that's 104. Right now, we haven't done sig figs yet. That's next section, but this is going to be 2 sig figs here, and so this is going to end up being have to have 2 sig figs in my answer. I'm going to say 1.0 times 10 to the 2. Okay? If you said 104 degrees Celsius, or rather degrees Fahrenheit, oops, that's this Fahrenheit. I don't know how to erase with this functionality, so I'm going to say degrees Fahrenheit. You'd be fine. Okay? So there's your answer for part B. Okay. Our next example, a man receives a ring he believes to be platinum from his fiancée. Nice. Before the wedding, he notices that the ring feels a little light for its size, and he decides to measure its density so he can decide if his fiancée is trustworthy and is worthy of entrusting, I don't know, the rest of his life. Something like that. He places the ring on a balance and finds it has a massive blank. All right. Mass, just a minute here. Mass 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters. 0.233 cubic centimeters of water. In other words, it makes a volume of 0.233 cubic centimeters of water. Is the ring made of platinum? Aha, there's the question right there. Here's the point. The volume of regularly shaped objects is often measured by the displacement of water. To use this method, the object is placed in water and the change in volume of the water is measured. And the change in volume is going to tell you what the object's volume is, right? The increase in the total volume represents the volume of water displaced by the object and is equal to the volume of the object. Okay, so this is the volume of the object. There's the mass of the object. We know that the density of an object is mass per volume. I think Tro uses a lowercase d here oftentimes. So let's calculate this. This is 3.15 grams, and this is 0.233 cubic centimeters. And by the way, the density of platinum, we know, is 21.4, right? We're amazed by that, in grams per cubic centimeter. Right? So if this density is 21.4, then the guy should go ahead and get married. If the density is not 21.4, the guy should jet his fiancée, find a woman worthy of more trust, and place his heart in her hands. So let's calculate this. 3.15 divided by 0.233. It turns out that the density of this object is really 13.52 and so on, right? There are 3 sig figs here, 3 sig figs here. So I'm going to say that this is grams per cubic centimeter. That's not good. That is definitely not platinum. I'm going to go back and look at that table before, which gave us the different densities. I'm going to find something. There it is right there. 13.55. Oh, wow. The closest thing to that is mercury, but since it's not a liquid, right, then it's likely a combination of a couple different things. But it is certainly not pure platinum. I'm afraid this guy's got some bad news.